So I need to say thanks for organizers and especially for Kevin for invitation. And it's very interesting to be in this conference because it is my first time participation in this conference, and I hope we will have a session about electrical machines in the next time. So I'm from Moscow Aviation Institute, Department of Electrical Machines and Power Electronics. And today I will try to introduce you some experience and some interesting projects of electrical machines with HTS windings in Russia. I want to start from the project of 200 kilowatt motor with HTS field winding. This project was started in 2011 when HTS2 tapes just arrived on the market. So it was a very ambitious project because there were a little amount of information about properties of the tapes, and during the project we have developed special technique of calculation of these machines and of manufacturing of them. The properties of tapes were researched, so their mechanical, thermal, and electrical properties as well. And this motor was produced and tested in 2015. So we spent four years from the starting of the project to have this motor. It has a warm starter with copper winding, cooled with water, but rotor is cold, and we used the rotating cryostat to separate cold rotor from the warm starter. And it was also another one challenge during this project because rotating cryostat is very complex part of the machine. But we have manufactured this machine in cooperation with our partners and tested it. And it was very interesting to estimate the critical current of coils. So each coil were tested during the manufacture, and then field winding was tested in the machine environment, and operating current was only 40 amps. So it was rather low value, but for this period it was very important to achieve this value because it was early steps of HTS2 tapes in electrical machines. So you can see low characteristics of the generator, and nominal rotation speed of it is 1,500 RPM, and the efficiency of the machine is 98% for nominal power. In parallel with the motor, 1 megawatt generator was designed and produced. It also has separated rotor and starter. So rotor is also cooled with liquid nitrogen and rotor is cooled with water. And this machine has 600 RPM. So it's a rather large machine with 1 meter diameter of the starter and 1 meter of the axle length. And you can see the comparison of this machine, which is the gray on this picture, and traditional one. So we often use this picture to introduce advantage of the superconductivity. And in comparison with motor, this machine has increased cooling time, which is around 60 hours. So due to large dimensions and big amount of steel, we need to spend a lot of time for cooling. Another one project is a close-shaped generator with HTS field winding. So it was also produced in 2015, and it has static HTS coil. And this is one of the advantages of this machine. So we do not need to to use rotating cryostat. And another one feature of the machine is application of permanent magnets, which are mounted on the rotor. So we did it to increase reliability of the machine. So if we, during operation cycle, we will have some problems with cryogenic system and superconductivity, and we will not have superconductivity. So this machine will provide half power with permanent magnets. So it has 900 kilowatt output power and 6,000 RPM and operates with 77 Kelvin. This project and two previous were made in cooperation with institutes in Russia and some manufacturers who produced these machines for us. And this cooperation gave us opportunity to develop not only calculation methods, but also manufacturing techniques, provide experimental research, because it was rather big machines with high output power. In MIE, we have a test bench only for 100 kilowatt. So when we're talking about megawatt class machines, we need to go to cooperation. So it was very important to have this experience in this period. So in 2015, we have developed such machines and goes to the next step, which is fully superconducting machines. So of course, electrical machines with HTS field windings can take their area of application, but from the point of view of specific power, they are not the best. If we want to achieve extremely high values of specific power, we need to go to ironless and fully superconducting electrical machines. And this is the project of a small-scale prototype of such machine. Here we have HTS field winding and HTS armature winding. Besides, this is the demonstrator, which we use to verify our calculation methodics and manufacturing techniques. And in this case, we try to have maximum from one machine. So this is, I can say, 3-in-1 machine, because in this machine we can have 3 different magnetic circuits. So the first one is the case when we have magnetic core of stator, magnetic core of rotor, and magnetic poles of rotor. And the second one, we have magnetic core on stator and magnetic core on rotor, but we have non-magnetic poles of rotor. Finally, we can have machine without magnetic core on rotor, only core of stator is ferromagnetic, and teeth on stator is always non-magnetic. So it gives our opportunity to verify our calculation methodics, because different magnetic properties of magnetic circuit have some features which we need to take into account during calculation. And in this case, this machine could provide maximum output power of 12 kilowatt for 2,500 RPM. In this project, we use AMSC tape with 5 millimeters width, and operating temperature is 77 Kelvin. So this machine is filling with liquid nitrogen, so rotor rotates in liquid nitrogen. And we have slip rings to have a current in rotor winding. And here you can see outer view of the machine mounted on the test bench. It's stator with HTS coils and HTS coils. And I need to say that HTS coils have support which produced with 3D printed technology. So it is another one feature of this machine. We tried to use new manufacturing technology in electrical machine, and as a result, this was successful. This machine work, and we still try to use another 3D printed materials in the machine. So here you can see also comparison of experimental results and finite element modeling. This is phase voltage of the machine, so it's for non-lowered and lowered regime. So you can see that they are in good correlation, and I can say that developed analytical and modeling approaches are give us a good correlation with experimental results, so we can use them to produce the high output power machines. Another one example of electrical machine which was produced is the machine with annular HTS winding on stator. So it's not an electrical machine in our traditional point of view, because the main goal of this project was to determine special test bench, to produce special test bench to determine parameters of AC HTS coils. And therefore, you cannot find the output power in the table with parameters of this with this test bench. So our main goal was to determine parameters, and this device provides us opportunity to deal it in the worst case of operating of HTS coils. So yeah, they are supplied with non-sinusoidal AC current. They are working in rotating magnetic field, which is perpendicular to the HTS tape. So that this is the worst conditions for the HTS tapes. And it gave us opportunity to measure AC losses in this machine, and we have done it. Here you can see some examples of results of AC losses measurement. So during the production of this device, we have measured AC losses on each step. On the first step, we have measured AC losses for separated HTS coils with sinusoidal currents with different frequencies and different values of current. Then we goes to measure losses with non-sinusoidal currents, which are BLDC current and BLEC current. So it is modulation of current, which used in electrical machines operates with power electronics. Then we develop methodic of verifying measuring of AC losses in assembled phase of the machine. Then we measured AC losses in the machine with rotor, but it was static rotor, so just in one position. And then rotor was rotated and AC losses obtained in all the machine. So here you can see comparison of losses when phase of machine supplied with sinusoidal current and non-sinusoidal current with BLDC or BLEC current, and comparison of the losses obtained with static and rotating rotor. So it is important to know that this machine were produced with IMSC tape, which have ferromagnetic substrate. So its values of these losses is rather high due to properties of HTS tape. Then the next project is the project of Hive 500 kilowatt motor produced by SuperOx company. Produced by SuperOx company. It has also separated rotor and stator. So stator cooled with liquid nitrogen, and HTS armature winding is applied. And the rotor have permanent magnets. So they have demonstrated this machine during last years, and it was interesting that they tried to manufacture coil with 8 parallel tapes, and think that they have reached success in this way. And the special construction of the cryostat of starter gives a low heat losses, which was one of the goal of this project. And they demonstrated this motor on the flying laboratory based on the Yak-40 airplane. And this superconducting drivetrain include motor, generator, fault current limiter, and DC cable. And they have presented it during UCAS conference and during the Moscow Aerospace Saloon called MAX this year. So we can say that today a lot of information about and a lot of experience all over the world about methodic of calculation of separated device, separated HTS device exists. But if we want to go to the system level, we need to develop special approach of calculation, manufacturing, testing of such systems. Because a simple addition of elements will not lead to the appearance of the system. And today, in cooperation with our partners, we try to make a system which is in general HTS generating system. So it consists of HTS generator, AC-DC rectifier, which is also called power factor corrector, DC HTS cable, battery, control and safety system, and of course cryogenic system. And we have two main goals in this project. The first one is to develop and verify methods of design of HTS systems and test them in different regimes. The second is to develop test bench, which will give opportunity for testing of different devices operating in coupled HTS system. You can see the main features of the system. It will have 100 kilowatt output power. And another one feature is that AC-DC rectifier will have the cryogenic cooling of power cascade. So it's our new step in the way of, in the direction of cryogenic electronics. And in this project, we have cooperation with different institutes, which is Institute of Thermal Physics in Novosibirsk. This is Joint University of High Temperatures in Moscow. We have partner which will produce the devices for us, which is TEMFAB, and also we have cooperation with Green Lab in University of Lorraine. So, and finally, I need to say that output voltage of this system will be 540 volts, which is perspective value for aviation electrical systems. And also this test bench could be used for long time testing of HTS devices such as generators and motors. And it's very important because I think that's the next step in the way in the HTS machine, in the field of HTS machines. It will be the testing operation for a long time period. So it's HTS generator, and this system will have a rotor with permanent magnet and HTS armature winding. It will be starter will be encapsulated and filled with liquid nitrogen. Rotation speed of the machine is rather high. It has 6,000 RPM. So if we want to rotate the rotor in liquid nitrogen, it will produce a lot of heat losses. So we try to separate nitrogen and air in which rotor will rotate. So in this project, we will use superox tape with 4 mm width. And output power of the machine is 90 kilowatts. And nominal value of HTS tape HTS tape current is 50 amps. Here you can see magnetic field distribution in the active zone of the machine. And it's important to know that value of magnetic inductance in the field of HTS coils is less than 1.2 Tesla. So according to field dependency of critical current, the critical current of these coils will be close to 80 amps, and it corresponds that for operating point we will have current 40 amps, so it's rather a big distance between operating point and critical current. So we will try to achieve the low losses in the machine. So as you can see in this machine, ferromagnetic core will operate with liquid nitrogen temperature, and you know that properties of magnetic steel will be different for room temperature and for cryogenic temperature. In this case, we developed a device to obtain hysteresis loop of steel. And according to the first results, we have increasing of saturation of the steel without increasing of losses in it. So from the point of view of specific power, it is important result because in this case we can decrease dimensions of ferromagnetic elements to increase specific power. So summarizing our experience in the field of electrical machines, we can say that today we have verified several calculation methodics and for different schemes of the machine, and we will go to the next level of the output power for fully superconducting machines. So in conclusion, I want to say that obtained experience gives us opportunity to go to the high power, high specific power machines, even with hydrogen cooling, and we're still working in the field of experimental research of AC losses of HTS coils in operating in different environments. So that's all from me. Thank you very much for your attention. I'm ready for your questions, and we always welcome you in our Moscow Aviation Institute in the Laboratory of Superconductivity. Thank you.
Thank you, Professor Ivanov.
The magnetization curve of the ferromagnetic material you showed us, and did you do these experiments at room temperature and 77K? Yes.
Do you mean this one?
Yes.
Yeah, we did it in the room temperature and in liquid nitrogen.
So which liquid nitrogen was better in terms of ferromagneticity?
Yeah, in terms of saturation, the steel is better in liquid nitrogen.
Did you publish this data?
Not yet, but we'll prepare the publication in the near future. I think that in January or in February.
Understand. I was looking for this data. I mean, I knew that there wasn't much difference. That was, at least it wasn't getting worse. But this measurement is quite good. Thank you very much for that.
I have one question, Nikolay, relating to that. Did you attempt to look at the mechanical property as well of the iron? How did you choose this iron for cryogenic application?
It's a traditional iron which we use for war machines.
Okay.
So the goal was to compare: can we use this steel in the cryogenic machines?
Okay. Yeah, there's a question if it is grain oriented or not.
Sorry?
Is it a grain oriented steel or not? The steel, is it grain oriented or not oriented?
This is the traditional electrotechnical steel with silicon.
So for rotating machine, usually it is not orientated, just for transformer. There is another question on the chat from maybe Professor Izumi. Can you read the chat, please, Nikolay, or you cannot see?
Yeah, I can see it.
So first question of Professor Izumi, please.
Is it for your design of 10 kilowatt full HTS generator? Is it no problems for the resistance to centrifugal force? Sun ponds and the rotational speed is high. Yeah, we
So
have special.
This is for Nakamura question you are replying, right? The last one.
Yeah, the last one.
Okay.
Okay. Yeah, this is Nakamura question. Yeah, we have implemented special wedge on the rotor which provide the cylindrical surface of rotor. Do you have any specific reason to choose the operation temperature to 77 Kelvin? Do you have any ideas to set other temperatures lower than 77, for example, 65? Yes. So the reason is very simple. It's the cheapest HTS temperature which we can achieve in our lab. So liquid nitrogen is cheap, and we can have it a lot without any closed loop systems or crack coolers. But of course, we have a lot of ideas to go to the lower temperatures, and I hope we will have this opportunity next year.
Nikolay, just related to that also, you know that you may use pumping to reduce the temperature bath, not using cryocooler, but just a classical pump. Did you thought about that?
Yeah, sure, but
it's still more complicated,
it's more complicated, and it's more interesting for us to go not to 65 Kelvin, but to 20 Kelvin.
Okay. There is one more question, and this will be the last question.
Very short one, actually. Did your cryostat have vacuum jackets at 77K?
No, we don't use vacuum chambers. We use special thermal insulation, a special construction of cryostat to apply it.
Thank you.